Hi everyone, and welcome to our last lab on electrostatic separation. The feed for this lab is a -28 mesh titanium bearing sand. It contains about 35% titanium minerals. It's important for this process that the material has a narrow size range, which we can see is the case. The black particles are the titanium bearing minerals that we want to target in this exercise. We are going to use a 2 kilogram sample for our process feed. Now let's take a look at the process itself. Important parts that affect the process separation are the rotor, splitter, and electrode. The electrode creates a voltage potential, which causes non-conductive particles to stick to the rotor. Conductive particles, such as the titanium ore, are not affected. The hopper dispenses the feed onto the rotor, which spins at a moderate speed. Since the voltage potential has little effect on the titanium, it is thrown and then can be collected. Splitters at the bottom of the device allow the operator to select where they want to make the split according to trajectory. Of course, the process is not perfect, and some titanium particles get pinned to the rotor, and some gangue particles get thrown. At the bottom of the device, 3 funnels collect concentrate, tailings, and middlings products. In this lab, I'm going to combine the tailings and the middlings into one tailings product. Products collect very slowly, as it is advantageous to only have a thin layer on the rotor for the best separation on this lab scale device. Besides splitter position, controls allow us to adjust the rotor speed as well as the electrical potential. Let's think about the separation and how our separation parameters will affect the split. So our separation parameters are, we have our rotor speed, we have the voltage, going to the electrostatic separator, and we have our splitter positions. Now, some particles, the gangue particles, attach to this rotor, ride the rotor around, and drop off somewhere here, ideally. Other particles, the titanium ones, just their inertia carries them this way. So what happens when we increase rotor speed? So we have 2 arrows now. Well, this is going to be going faster, these particles, and they're going to be going further. However, there's some force holding these gangue particles on, and now that the rotor's going faster, some of these gangue particles might also be thrown off of the rotor. So if we weren't collecting the material in cups and they just made piles on the ground, with a low rotor speed, maybe you might get a pile of gangue here, and you might get a pile of gangue of the titanium here. With a higher rotor speed, you're going to get a wider distribution of the gangue material. And your titanium also gets thrown further out. So the titanium shifted, but initially you had a better separation. If you drew a line here, you have more mixing in gangue than if you drew a line here. So in some ways, we're able to throw our titanium further, but we also might recover more gangue. So there's the positives and negatives. What about our voltage? Now, that's going to allow us to have a higher force keeping these particles attached to the rotor, the gangue particles. However, if you put it up too high, you get arcing, and that makes the process inefficient. You want to get as close as you can to arcing without actually arcing. So, assuming you're not arcing, let's say you let the material pile up. Gangue's here, titanium's here. Titanium, this isn't going to shift if you put the voltage up. But what you might see is more gangue attaches to this rotor for a longer period of time, less flies out, and the titanium you'd hope would look the same. So we probably want to keep our voltage as high as possible without going over this threshold. Now, the splitters dictate where these piles are separated. So for a given rotor speed and voltage, you would make two piles on the ground. The splitters dictate where you would split. Do you split here, there, there? It's hard to tell. It's going to require a little trial and error. The first step I'm going to take is to reduce the amount of feed going onto the rotor to make a better separation. In a real process plant, however, one has to calculate if a reduction in feed rate and therefore production rate is economically viable. We also have some arcing, so I'm going to turn the electrical potential down. I played with the rotor speed a little to try and throw the titanium particles further, but it's hard to see them, so I didn't change it too much. I don't want to throw too much gangue over the splitter. I left the splitter a little below the mark that was drawn on there. I'll trust whoever drew it. Now we just collect their samples. Here you can see our products. This one on the left is the concentrate, and on the right is the tailings. The left product is a little darker, but the separation isn't so great. Organized test work usually beats out guesswork.